Hello, everyone. Thank you for joining us today for our webinar presented by the Asset Integrity team at Stantec. My name, Dennis Zadri, Vice President of Asset Integrity at Stantec. So this is actually a follow-up session to a webinar we hosted last spring in May of 2020 regarding the commercial and process considerations of hydrogen in the industry. Today, we're going to be focusing on gaps in code coverage for hydrogen that's less than 10% in operation of pipelines, and really focusing on the implications for design, materials, and integrity management of systems that are going to have blended hydrogen. We all know how hot a topic hydrogen has been over the last year or so in the industry, and this webinar is going to dive into some of the considerations and implementations of adding hydrogen to your system. Today's safety moment is quite applicable to the topic. We're going to talk about gas appliances in the household. So some great images here of those devices that we'd all see in our homes: natural gas fireplaces, stove tops. Most of us have a barbecue with either natural gas or propane hookup. So just some of the reminders that understanding the safety part of these systems, making sure all the connectors and the lines are checked on a regular basis for leaks, making sure we know where the shutoffs are. I read a great online story about understanding how you could turn off your mainline gas shutoff in case of emergency in your house. I'm not sure how many of us have practiced that or ever tried it, but if there was a leak in your house, it would be one of the first course of action you want to do is shut off your main shutoff to your gas supply. And just making sure, like your furnace and your water tank, you get an inspection done on a routine basis, whatever that might be, maybe not yearly, but certainly more than once every 10 years. And understanding that, the basics of changing filters on the furnace and dealing with any other appurtenances or connections to the hot water heater and the furnace. So that's good for all of us, since all of us have to deal with these appliances in our houses. I already introduced myself. So our two lead presenters today are Christian Olsen, who has both a bachelor's and a master's of science in materials engineering from the U of A. Christian is over almost 25 years of industry experience in asset integrity and materials and metallurgy. And our second presenter is Jonathan Prescott. He also has a bachelor's degree and master's degree in materials engineering from the U of A, and over 14 years of experience in areas such as asset integrity, fitness for service, and pipeline design. Take it away, Christian.
Thanks, Dennis. I'll just move the slide here. And I might need some help just to go to the next slide. Thank you. We'll just start with a poll question here from the audience. So just answer as soon as you can. The question is, what is the biggest barrier to hydrogen blending in your area of work? Is it economic or regulatory? Is it about primarily integrity concerns, or is it all of the above? Okay, I don't need help from Jerry if right now I don't see the answers. Okay, there we go. So it's kind of split there, all of the above, and then also integrity, close second. And that makes a lot of sense. It seems like this transition to hydrogen is complicated on many levels. Integrity is one critical, but just one part of the problem. Okay, so I'm going to start the presentation here and then hand over to Jonathan. And really my objective is to just provide a common language for an engineering basis that we would use for assessment work. Next slide. And at the end of today, I'm hoping we can walk away with being clear on two items. The first is understanding which codes and best practices help us assess and manage hydrogen risk. And the second is about how we can recognize and address pipeline deficiencies before we're adding any hydrogen. Going to put together a bit of a gap analysis here. On the x-axis, we would have hydrogen blend rates, and then on the y, we would our vertical would be the pipeline pressure. Next slide. Next slide, please. Thank you. Oops, so we'll start with what we have today. It looks like I have control now. That's good. Obviously, we have pipelines, say in North America, built to either ASME B318 or in Canada, CSAs at 662. going to focus primarily on the US codes just for simplicity. We can talk about exceptions as we go along. And within B31.8, if we're looking at pipeline pressure, there's a rough delineation for most pipeline sizes at about 40% of the specified minimum yield stress of the material. Above that, of course, you still have to design to 31.8, but you have a fracture toughness criterion that you also need to include in order to mitigate higher operating risks there. Both of these codes are not hydrogen codes, at least not today. And so we're really just centered on that vertical axis for now. Okay, that worked. But when we look at hydrogen, well, we have ASME B3112, which could be argued is applicable for both US and Canada for various reasons. And what we see is that there's a similar delineation. There we go. And that delineation is at the 40% SMICE value, above which we have a fracture toughness criterion like B31.8. It's just a different criterion, and for the same reasons. B3112 is a little different though than 31.8 in the sense that it is paring down the list of allowable materials to what it considers hydrogen compatible. So we're not going to see an X100 pipeline steel there. And while it can push people towards much lower design stresses, doesn't have to be the case. Probably the most infamous part of this code is the B31.8 conversion rules, which are extensive, but that's what they are. And finally, modifications to integrity programs and integrity work. I just want to quickly say that in the same way that Stantec helps its clients every day on gas pipelines with 31.8 or Z662, we can definitely help you either with conversion or even design and operation and maintenance of hydrogen lines. But if we look at so far, we already have a gap in the code, and it seems to be, say, between that 0.1% and 9.9% hydrogen level at any stress level. Okay, now we've talked about the code and some gaps. I want to talk a little bit about what hydrogen embrittlement is. We think about within our pipeline, we have, diatomic hydrogen molecules here. And then we have, other things like methane and some impurities. And the diatomic hydrogen has this special ability at ambient temperatures and pipeline pressures to absorb to the surface of the steel and then actually dissociate into atoms, or if there's a corrosion reaction, maybe even protons. And then they're wandering around in the steel. So this would be a normal occurrence when you have hydrogen gas. The problem is when they all of a sudden start to find spots and interfere with atomic bonds, say between the iron or the carbon or manganese that's in the steel. And that's really embrittlement. It's interfering with those bonds, at least for the purposes of this presentation. So while we said diatomic hydrogen can split apart and diffuse through the steel, that's not the case with methane. And as far as the other sort of molecules we would see in a typical a gas pipeline, well, some can make things better or worse. Most famously would be the oxygen level, which is a whole different topic, but that can be a real game changer, it seems, as far as actually mitigating embrittlement. And we can definitely talk about that offline. Things like water could be good or bad, depending on how you look at it. And again, that's something we expect to see a little bit in our gas streams. A bigger point here is that every day we're using tools to help our clients in the natural gas world, looking at probabilities of failure, and we're using tools that are actually just as applicable to hydrogen. So some notable examples are API 579, Chapter 9. Which we do, we have a lot of experience with these codes, the different API standards, ASME, including Section 8, Division 3, the article KD10, and of course, different NACE standards, stuff that we might use for sour pipelines, for example. Okay, so that was embrittlement. Just want to delineate between that and damage. Here, hydrogen damage, well, there's three main forms, two of which we would expect to see it maybe at some extent in a pipeline, or at least we want to be looking for. So this first would be HIC, or hydrogen-induced cracking. Remember, we have these, single hydrogen molecules that are wandering around inside the steel, and they can sort of pile up in areas where we might have a lamination, and then recombine in some cases to diatomic hydrogen, which is a lot bigger molecule. And so we're really forming a wedge here that can start to, grow cracks. And if they're extensive enough, they can sort of grow into each other and form a stepwise pattern. Similarly, we can have SOHIC, stress-oriented hydrogen-induced cracking. And so typically we would look for this, say, in a heat-affected zone near a weld. That's a microstructure that can become susceptible to hydrogen recombination because it has an applied stress level. And so in this case, we have a hoop stress that's working to pull the weld apart. We would see the heat-affected zone near the weld metal, and we'd see cracking that was perpendicular to the stress. And while it's debatable if we would see this in a dry gaseous environment, I do just want to mention hydrogen blisters. In a sense, it's like HIC, but the amount of recombined hydrogen is so severe, it's actually forming a bubble. It's pushing, a layer of steel apart. And again, we have tools to look at and assess this sort of damage today. This is API 579, Chapter 7 as an example. Just trying to move to the next slide. There we go. So we've talked about embrittlement. We've talked about some damage. I want to just bring it back to, again, a common language on how embrittlement can affect the engineering properties that we use to do an analysis of probability. I'll start right with the basics, with a tensile sample that we would expect on any steel that we're using in our pipelines. Of course, we can machine out a coupon and then make it into a dog bone shape, and then we pull on either end. And we really have three regions of response to the strain, which is stretch under stress. In region 1, we have this elastic behavior. It's just like a perfect spring. But if we pull hard enough, we eventually get into region 2, where two things are happening. So one, you can see we get this local deformation that's called necking on this coupon or the sample. And in there, and partially throughout the whole sample, we're going to get some cold work, or work hardening. So the steel's actually getting stronger. And at first, that work hardening actually wins the day. We can accommodate higher stress, but to a point where the reduction of area is so much, it eventually snaps or breaks. And that's at the point of failure. And of course, I really exaggerate it just for example. We'll quickly mention that strain, the rate of strain, how quickly you pull matters, and of course, even more so with hydrogen. Of course, we have names for this stuff. We have a yield strength, we have an ultimate tensile strength, and a flow stress, which would be typically a average of those two. And then we have two other parameters here, which, while they are different, really speak to the ability of this alloy to fail gracefully. And that would be the strain at failure, or percent elongation, and the percent reduction of area. I want to contrast this to, say, a pure brittle material. This might be like glass, or even in cases like a composite material, fiberglass or carbon fiber, where you can see, and this is what scares engineers so much using truly brittle material, is we're basically staying in region 1, and depending on the flaws or geometry, stress risers, we can all of a sudden, it'll just fail. And we need to account for that, with certain conservatism. And so the big question is, well, what's embrittlement doing to a normally ductile steel that fails with grace? How far are we moving over that way? So here's an example. I'm taking this from Hydrogen Tools website that quotes a lot of government data as example. We're looking at just comparison here between an X52 pipeline steel and an X70 in all cases. The blue bar is the test done in air. And the orange bar would be the test done in about 7 MPa hydrogen or 1 KSI hydrogen partial pressure. Tensile strength values don't change much, nor do the yield. It's all within about 10%. The alarming values for relative difference are elongation and reduction of area, and some of them are pretty big. So yeah, that's not great. I just want to underscore that even these embrittled values, 15% elongation isn't too bad. For example, this is about 38% reduction of area. So we are more still ductile. We're just moving towards this. And Jonathan's going to show the implications of that in some examples. Something else that's been noted with tensile samples is if you have a notch or some flaw and you're pulling that, the samples do a lot poorer in a hydrogen environment than air. Of course, we have a whole field of study for this is fracture mechanics. And just as an example, if we have a section of pipe with a long seam weld, and there's a flaw of known geometry, this happens in pipelines, and we have a hoop stress that's applied really to pull that long seam weld apart. Well, we can model this by calculating a stress intensity. We know that intensity changes with increasing hoop stress or pressure, as well as the crack size or the flaw size. And so here's an example where we take a constant pressure and we would plot the severity of the stress intensity versus that depth of the crack. And ideally, if nothing else, we want to make sure that that value is less than the demonstrated fracture toughness of our steel, which by the way in B3112 would be about 55 MPa root meters. So here's an example if we're looking at some fracture toughness value. I told you that strain rate matters, and I picked something that was, kind of a worst case from Hydrogen Tools. And we're looking at two alloys. One would be X42, where we see quite a few data points, and X70, just a couple to overlay on this. Take this with a grain of salt. There's a number of different methods used to calculate this, but we are seeing a trend with fracture toughness as it starts in air and then degrades with increasing hydrogen partial pressure. So here's a 9.9 kPa, so 10 MPa line, say, or that would be 1440 psi operating pressure. And if it was 100% hydrogen service, we could expect about a 60% drop in the fracture toughness. They do start with nice values or high values though, but 60% is still a lot. And if we're talking about it, say a 10% blend, that would be about 10% loss. Another thing that we want to understand is our fatigue endurance or fatigue life. And so here I'm just showing an example of something done in air. It's from a French study where they compared air and hydrogen. And so here we see there's two big components to fatigue endurance. The first is the ability of a part to withstand a stress, say that's above a threshold value, to withstand that without any sort of fatigue cracking forming. It's all microscopic damage at this point. And then all of a sudden we do get a fatigue crack, which initiates and then grows. And if it's left growing, it will eventually fail. And of course, in a pipeline scenario, we do have fatigue cracks that sometimes happen, and we need to monitor them and fix them before they become a problem. So this French paper, it's the reference is below. They're part of sort of the European initiative, I think, Natural High. They're looking at pipeline blending in that part of the world. Unlike all the other data I'm showing you here, they're actually using hydrogen that was charged electrochemically. So that's a bit of a caveat because it may not truly represent what we see in our pipelines. But if it does, we see two important bits of data. One is that our overall fatigue life drops substantially. This is a log plot, so it's a big drop. And the other is that the percentage of this fatigue endurance life is actually smaller. So we have a little less cushion. Only 20% of the life is with a fatigue crack growing versus 30% as before. So then I'm going to go back to some data. This is just a sketch of data you can find in the paper below. This is from a group that actually provided test data for ASME 31 code, 3112 code body. The sketch shows that we have this, roughly linear response of the fatigue crack growth rate, so millimeters or say inches per stress cycle. And so it's growing, and this is on like a log plot. And I will say that, based on this paper and other references, what we see is that if you're X42 or X70 pipeline steel, it doesn't seem to matter. All the data seems to be lumped, grouped around, this blue line. But what does matter is if you start to add hydrogen, and it could be any amount of hydrogen, maybe just a few PSI. If you get above a certain, stress intensity level, that growth rate in millimeters per cycle can go 10 times as higher. And then it will stay that way for the remainder. So this is definitely an item of concern. If we can have a big jump in data that happens with a small amount of hydrogen addition, and that seems to be more important than the actual grade of the alloy. So just in summary here, we talked about some code gaps. It seems to be that between that 0.1% and 9.9%. We could argue in engineering assessment, if we're looking at higher than or 10% level or higher, that we do have existing code guidance, in North America that we would use for engineering assessment. And then the question really is, if say we're going to blend at 5 or even 9% in our engineering assessment, when does it make sense to use what we have in B31.8 and maybe augment that or just show that it's safe? And when do we need to start borrowing, some of the guidance from B31.12 to be safe also? And Jonathan's going to talk a bit more. If we look, say, at something that's a relatively high stress level, relatively high amount of hydrogen gas, how does our pipeline perform when we're talking about fracture mechanics or fatigue life, or even, dent or gouge? So I'll give it to Jonathan now.
Okay, thank you, Christian. That was very nice. Why don't we kick things off here with a poll question. At what stage is your organization in the conversion to blended hydrogen? Regulatory or market studies, feasibility or material studies, material verification or upgrading, and actually transporting blended hydrogen or blended natural gas. So I'll let that run for a few moments. And while we're getting those poll questions, I'll just let you know that I do have a digital set of notes here, and I will be going back and forth and advancing 2 different sets of slides. It might take 1 or 2 seconds to do that. And I may occasionally sip on some water. And you'll hear a pause. Okay, some very interesting results. I think that that says it all right there. No one's yet transporting blended hydrogen. We are basically trying to figure this thing out together. Okay, well, the purpose of my slides is to kind of build on Christian's introduction. We just finished learning a lot about some of the material property degradations, and now we're really going to explore, how does microstructural hydrogen, so hydrogen that's in the crystal lattice, how does that really impact our fitness for service calculations? And so we don't have too much time to go over every type of imperfection, but today we're going to just take a quick look at metal loss, a dent example, and a few cracks. Okay, so before we begin, we're going to need to take a look at a particular pipeline configuration for the calculations. So let's just take a look at that here. On the left side of the graph or of the presentation, you'll see that we have an NPS 24 pipe, and we want to introduce just a small amount of hydrogen, let's say up to 10%, just below, at 6,700 kPa. We have a 7.92 millimeter wall thickness, API 5L grade X52 pipe. And we'll also assume that we've gone ahead and qualified our material or have sufficient material records to show that we have the following material fracture toughness properties. So in air for base metal and long seam, and in hydrogen at a 10% blend rate, we lost about 10%. So we still have 90% left. Some of the other assumptions that we'll have to make here, we want to take some guidance from ASME V3112. We want to carry out kind of a similar type analysis to option B, where we do a performance-based evaluation. Here are some design factors: 72% SMICE line, joint and temperature factor of 1. And that really, we're just looking at a pipe that is not near any high consequence areas, class 1 division 2 location. And we'll do that, we'll look at the metal loss and dent and crack under pretty much this sort of operating scenario where we may have a moderate cycling, and then there's a summary table showing comparing to light cycling. For crack growth rate, we went ahead and compared the crack growth rates in B3112 as well as the crack growth rates for, say, SEC and 579. And we have a crack example for SEC, and we've taken the worst case growth rates from the two. Okay, so before we move on to the examples, another thing that we just have to understand, we have two important concepts here. We have Dalton's law of partial pressure. So the total pressure in a system is basically the sum of the partial pressures of the gases. And that partial pressure is related to mole fraction. So here we have basically 10% hydrogen. So it's contributing basically 10% of the total pressure. We also have another important relationship, Sievert's law. And that law dictates the concentration of dissolved hydrogen atoms in a solid as a function of the square root of the pressure times a constant. And for hydrogen, we find that this constant is sufficient enough that we get an appreciable amount of hydrogen even at low pressures. So what do we need to understand? We need to understand that as we increase our mole fraction in our blend, our hydrogen partial pressure is going up. The amount of dissolved hydrogen in our microstructure is increasing. And of course, if we have more hydrogen, we have more material embrittlement. Okay, our first example, metal loss. Many of these slides are structured in a similar way. What you'll find is there is a throwback basically to Christian's section where we present the degradation or the change in the material properties in hydrogen service versus air. So here you'll see on the y-axis that we have the ratio of the flow strength in hydrogen versus the flow strength in air at a number of different grades here, covering approximately grade X42 to kind of X80. So it's represented by flow strength. What we see is that we have no data points in this small data set that is below 0.9. So one possible approach for our fitness for service would be to simply introduce an additional partial safety factor for hydrogen service. Here I'm showing you the modified ASME B31G failure stress equation with that new partial safety factor. And what you can see is the influence of that new partial safety factor on our metal loss critical defect curve. allowing less, not so deep and not as long features. Of course, if we increase our flow strength, or had we had a higher grade, that is also pushing this curve in the opposite direction. Okay, let's take a sip of water. Okay, so this is an example of dense. You'll see 3 graphics. Let's start with this top left one here. The purpose of this graphic is basically just to highlight some key differences between the B31.8 code and the B31.12 code. You'll note that I'm not listing all the criteria in the code, but I'm just highlighting the differences in the strain limits. So in the B31.8, for pipe body, strain limit is 6%. In the new B31.12 code, it's 2%. At the girth weld in B31.8, it's 4%. And again, remains at 2% in the B31.12 code. So I'll draw your attention to this graph down here. When I first saw this graph in the literature, I thought it was a very interesting graph because it really kind of tells a pretty good summary of what's happening to our material properties as we're increasing hydrogen. You'll note that, as Christian mentioned, the yield strength, the tensile strength, and thus the flow strength and strain hardening, and even the uniform strain limit basically remain the same within kind of 10% of their original values. And where hydrogen is really influencing is in the total ductility. So as we increase the partial pressure of hydrogen, we're saturating our microstructure with hydrogen, and this really influences the nucleation growth and coalescence of voids in the microstructure, resulting in much more severe cracking much sooner than we would otherwise expect in air. So you'll note that even here, we have here 1.7 megapascals of hydrogen, and that for our example, we're just, maybe a third of that or a half of that at 0.6. And so these new limits, they may be for much higher pressures of hydrogen. That's what it appears to me anyways. I believe the safety factors are most likely taken off the uniform strain limit, and that as our industry kind of bootstraps itself up here with blended hydrogen, we may see some refinements to these numbers over time. I'll draw your attention now to this final graph, but before introducing it, I'll note that in CSA, we have the ability to always perform an engineering assessment on a dent, and that's ultimately what governs whether we should repair it or recode it and place it back into service. And there are recommended practices out there which detail various advanced analysis techniques for understanding the nature of these strains. So here I'm presenting a technique out of API RP 1183, section 8.2, dent formation induced cracking potential. So each one of these little red dots here is a little element from an FEA model. So in this graph, we actually take a pipe, we indent it and deform it, and we track the true strains. And it's only strains that combine in a certain way that lead to cracking. And so when you are above this line here, which is 1, a crack is formed, but we also apply a safety factor on top of that, 0.6. What we might see in the future is there might be a case for introducing an additional partial safety factor for hydrogen surface at low blend rates. That remains to be seen though. For now, it would be very prudent to simply just follow the limits from B31.12. I'm just gonna take a drink of water. Okay, I have 4 crack scenarios, and I just want to go back to the metal loss here. Envision this as a critical crack curve instead of a metal loss defect curve. The 4 scenarios that we're going to look at is small depth, small length features, and then we'll increase the depth a little bit on one of the features, and then we have 2 other features that are a little bit longer. So we're kind of well within an acceptable size for initial starting features. So here we see the first 2 features, feature at 25% deep and 50% deep, not very long, less than an inch. And we note that at various stress levels between 10% and 72%, these features, even in air and hydrogen, are quite acceptable. We're in our acceptable region. And the failure mode, had we continued to increase pressure, would be collapse controlled. Here you see the throwback to Christian's section where we note that with a 10% hydrogen blend, we still are able to hold 90% of our original fracture toughness. So here are the other 2 crack features. We'll call them a pipe body crack and a stress corrosion crack, starting at 2.5 millimeters and 1.5 millimeters, but quite a bit longer in size, about 4 inches and just over 5 inches. Again, we note that they remain within the acceptable region of the FAD under our operating conditions, even with the 90% fracture toughness, which basically made the lines go from down here, the dotted lines, or the blue dotted line to the orange dotted line, and the blue solid line to the orange solid line. So not much change. Okay, well, those are for our initial crack sizes, but what about how these features perform over time? Christian told you about how introducing any amount of hydrogen, even very low amounts of partial pressure, makes its way into the microstructure and finds its way to crack tips, and that results in almost an order of magnitude increase in crack growth rate. And that's what we see here on these graphs. We see that we have this blue line indicating the remaining life in air for the 2 features, 25 and 50% deep at just about half an inch, and how significantly they are influenced by that new crack growth rate. So we note that the influence of hydrogen on crack growth is quite evident, and that for a deep flaw, it may lead to a remaining life, which is hard to manage from an integrity perspective. It doesn't seem to get any better for long features. Here's a feature that basically failed prior to reaching 80% depth. That's our pipe body crack at 139 millimeters, and under hydrogen service, barely lasts a year for moderate cycling conditions. The SCC feature, which we grew with the worst case from B3112 and 579 crack growth rates, due to it being a little bit shorter, had a little bit longer life than the other one. This slide provides you with a comparison. The previous graphs didn't have the light cycling on them, simply to make it less busy. but here we'll note that the remaining life in air versus hydrogen for light cycling and moderate cycling. So we note that under moderate cycling conditions, those features that we had have very good remaining life. We see the influence of the increased crack growth rates. However, we'll note that under light cycling conditions, we are seeing some amount of remaining life that we may be able to actively manage and operate a pipeline safely. So I think this really shows us that there's room for smaller dimensional features under light pressure cycling conditions to exist within hydrogen service, and that they give enough remaining life for integrity management. And of course, we just presented 4 examples, but you could easily go through the exercise of generating critical crack curves as a function of remaining life, whatever remaining life you feel is important to your organization, whether that's 100 years, 80 years, 40 years, etc. Okay, before I move on to integrity management system considerations, I'd just like to summarize that we saw that the crack growth rate is not linear. It's a log-log plot, and it increased about 10 times as our stress intensity increased as long as above that transition point. That the crack growth rate is influenced heavily even at low partial pressure hydrogen, but it seems to be manageable if we can manage the pressure cycles on a pipeline. Right now we have very good crack management programs. We have a lot of guidance from API RP 1176. And we'll note that the crack growth rate is essentially proportional to the imposed cycles. So we note that pressure cycling is a key operational parameter to keep a close eye on. One other thing to note is that the TTO number 5 pressure spectrums, in my opinion, and based on my experience with certain gas lines, can be quite conservative, because I believe those spectrums are designed to be conservative, and they often come very near compressor stations. And so if your pipeline is quite long, then you may benefit from the damping effect of the compressible nature of the gas, and that for cracks that find themselves further down the line, you may find that you can have deeper features and longer features without it being a problem. Okay, let's move on to discuss some integrity management considerations. Here, we note that in B3112, there is great guidance on what to consider for conversion. I've tried to present here a graphic that really kind of captures the essence of a lot of the elements discussed in that part of the code. The elements really categorized in terms of design, material, and the condition of the pipeline. So we note that at high stress levels, we can have issues with stress-oriented hydrogen-induced cracking. And so we need to pay close attention to the kind of the layout and supporting support structure, as well as differential settlement in our facilities. The material, we need to perform adequate historical material testing, or have sufficient records to kind of prove out our material. We want to have enough confidence in our material properties and the base metal, heat affected zones, girth welds, and that really want to pay close attention to the condition of the line. We've just seen how imperfections can be negatively impacted by the introduction of hydrogen. Okay, so what can we do about it? Well, we can leverage our existing codified knowledge. We have, as Christian mentioned, many great standards and recommended practices out there in the industry that can help guide us. We have, of course, our engineering judgment, and we have lots of research, new research knowledge that has been published in the last 15 years that can help guide us. And of course, we, as integrity engineers, are quite familiar with how to address threats and respond to threats and manage those threats over time. We may have been involved in reconditioning a line, bringing it back into service, so reactivating a line, increasing pressure on certain lines, and even changing service fluid, maybe going from sweet service to sour service. All of that knowledge can help us in preparing a pipeline for hydrogen service. We note that our integrity management programs are, in my opinion, very sophisticated. Many pipelines are on their second or third high resolution inspection runs. And if we find that any of our pipelines have gaps in the data requirements, then to prepare for hydrogen service, we should go out and conduct inspections. Here you're being presented with a variety of different inspection technologies that are available in the industry and what they can capture from an imperfection perspective. I'll just advance here. Okay, so the possible required mitigative actions. We may have to correct any design deficiencies. We may have old facilities that have high stress areas. Perhaps we've had a high degree of cold bending or differential settlement or some other natural process over time that has caused high stress in our system. We may have incompatible equipment we need to look at. Of course, there are certain things that we may need to pay close attention to, like susceptible microstructures, particularly for vintage pipes. There's been documented failures related to hydrogen-induced cracking for vintage pipes, and there's no real no assessment technique for that other than to essentially remove those susceptible microstructures from the system. And of course, reevaluating all of our failure stress and remaining life for hydrogen service. And we noted that for metal loss, we may need to introduce an additional partial safety factor. For deformations, it seems like perhaps we can continue on the same path of performing strain assessments with caliper or using FEA to get our strain and simply comparing those strains to new strain limits. All right, back up here. For crack-like features, we may have to remove certain very deep features or very long features out of the system because of low remaining life. And we may also have to pay close attention to pressure cycling. So in conclusion, I think Christian and I have presented here today that hydrogen can have a significant influence on the material properties, even at low partial pressure and low blend rates. The crack growth rates appear to be the most susceptible and substantially increase by an order of magnitude. We've kind of gone over some potential areas of concern. Susceptible microstructures, I hadn't talked about laminations. Laminations can always also be a problem, particularly if they're sloping or interacting with other features, surface laps. We are concerned about areas of high stress and strain history, and of course, the existing condition, all types of features that could interact with hydrogen. You know, we note that pressure cycling and how we operate our lines is an essential variable. Talked about how the crack growth rate is directly proportional to the amount of imposed cycles on a pipeline. So we should play with the levers that we have. We should reduce the amount of cycling as much as we can. And that the data really suggests in the literature that we need to be concerned about hydrogen at any blend ratio. And of course, we've explored, at least from an introductory perspective, for a few types of metal loss, a few types of imperfection types, what we may have to do to modify the fitness for service techniques, either by accounting for degradation in mature properties or introducing additional partial safety factors. Okay, that takes us to the end of the presentation. Hope you enjoyed it. I would like to ask us some questions. Back to Dennis for now.
All right, Jonathan, Christian, thank you for that comprehensive overview of how hydrogen can impact materials performance. We do have a long series of questions. I'll do my best to get to as many as I can. If we don't answer them all on this session here, everybody, we will get back to you offline because there's a great variety of questions here for both presenters. So I'm going to start with you, Christian. Question number 1. We talked a lot about existing infrastructure. If we're talking about brand new build for a hydrogen carrying pipeline, it doesn't matter what percentage of H2 content, does a corrosion resistant alloy cladding resolve most of these issues with critical H2 anomalies? So that would be a new build with a more sophisticated CRA alloy. Would that change any of these scenarios, Christian?
Perhaps. There are a number of materials that are not something you'd want to use, like nickel alloys that you might see in, instrumentation tubing. CRAs, of course, are extremely expensive, and it would seem that the best option for any pipeline is just the use of approved carbon steels in B3112.
Yeah, I think this might have been specific to cladding or coatings, and there's another question similar. So any thoughts about claddings at all, Christian?
Well, we've seen evidence that certain barriers can be added to a steel to greatly inhibit the diffusion of hydrogen into the steel. So there's definitely some potential there. I don't know which ones would be economical or not, but that's definitely an area of research and possibility.
Okay, I'm going to stick with you, Christian, for the next one. If actually go back to the presentation, slide 19. So I don't have it handy right now, Christian, but maybe you can look at your slide 19. The question is, what percentage of hydrogen was used in that particular evaluation or assessment?
Going off memory, but within H2 tools, there's a write-up from Sandia National Labs. They take a lot of data, and there's a particular chart in there you can find where they're showing, was it 0.02 MPa hydrogen? So they show.
What was slide 19? What was that graph all about, Christian?
So it's the effects of fatigue crack growth rates. And I think the question is really about if we have, I don't know if I can find it, but a small amount of hydrogen, how small before we start to see this big leap? So within that reference, you'll see a table, and it's this carbon steel compatibility, and they show a line in air and then a line with various amounts of hydrogen and carbon steels. And so I believe it was 0.02 MPa hydrogen where they saw a big jump in the fatigue crack growth rates.
Thanks, Christian. Jonathan, I'm going to jump to you, and this one just came in recently. Fatigue life is a consideration, but is it an actual real problem for gas lines? Let's be honest. In a lot of existing natural gas lines, we can get 100-year fatigue life out of certain size of features. If hydrogen only decreases that from 100 to 80, hypothetically, would this actually be a real impact on our integrity management programs going forward?
So, okay, I'm not on mute. In my experience, it almost seems to be needs to be handled on a case-by-case basis, on a kind of a pipeline-by-pipeline basis. And kind of where that feature is in the system. If it's very near a compressor station and it's a moderately cycled line, then what these calculations are indicating is that it could be, you could be seeing quite a bit lower remaining life. And And it's not like 100 years to 80 years. It's like 100 years to like 10 years. But the further you are away from the compressor station due to the compressible nature of the gas, there is some ability for the gas itself to absorb the pressure cycles, and so we can capitalize on that for sure. And we may find that for features that are really far away, that there's almost no cycling at all, and we may get the same performance in a hydrogen application, versus just pure natural gas.
If you don't mind, just add to that, we understand that pressure cycling is just one way to induce cyclic stresses to a pipeline system. We also have, the mechanical cycles, and so those are different. We were just trying to present something that was, we could manage in a 40-minute presentation.
Thanks for that answer. Agreed. So there could be concerns, Christian and Jonathan, but yeah, as you said, could be case specific to the age, vintage of the pipeline, and the pipeline's past history with cracking, let alone what it would look like with hydrogen blend.
Mm-hmm.
I'm going to blend two questions together here, Christian, that kind of have the same tone. One is to do with leak detection. So in a natural gas line, if it leaks, they have odorant and they can detect it. So with hydrogen line, whatever percentage of blend, what can be done for leak detection? But a second part of that is, can you talk anything about the safety concerns of hydrogen leaks? So if a hydrogen line was to actually leak or explode as opposed to pure natural gas, is there any difference in the outcomes?
Well, from what I'm hearing, if we're talking about low blend rates, well, we basically have, natural gas that has an odorant in it. And so we still have that level of protection. If we're talking about, substantially pure hydrogen, because it's almost all hydrogen or because we need it for certain application, I have seen some references in the literature about, research for odorants. But I think we have to look at other ways to protect, or prevent leaks. And I think about my experience in refineries where certain types of connections we just don't allow. We make sure we're doing things that just inherently are more safe against leaks. And of course, that gets into the whole area of polymers or non-metallics, where the principal concern is diffusion, and the rates of diffusion of hydrogen can be much higher than natural gas. So especially if we're in a confined space, that could become an issue.
Yeah, thanks for those answers, Christian. Yeah, good references. We are running out of time here. I realize we're almost up to the 1 hour. I'm going to do a couple more questions for the audience and Christian, and then at that point, we appreciate most people have to log off and we'll be closing off here, but I'll just try to get these in here. So I'll go with you, Jonathan. 20% by volume hydrogen is often considered to be okay without changes. I know you talked about the 10%. Are there significant considerations that should be taken prior to moving to 20% and beyond? You spoke a lot about 0.1 to 0.9%. 20% and beyond, does that change the story totally?
Well, even with so I guess at the end of the day, it's because we are benefiting from being a blend and having a lower partial pressure. What I've seen in the literature that often refers to, say, 20% being acceptable is they're often starting at a very small initial feature size, almost a feature size that's grown right out of a kind of a sound microstructure. And it didn't seem that there was any consideration for other types of features that may have been either placed into service or that have grown in service, for example, like stress corrosion cracking. And so, I'm a little bit hesitant to say that, okay, just go and blend 20%, because really you have to look at what you have. I mean, if you've got a 4-inch SCC feature, then hydrogen is, we've just shown here that it's not going to last very long.
And of course, we have a code body B3112 that specifically gives its scope as 10% and higher. That means something.
Agreed, Christian. Okay, last question, it's a little bit general. Is any learnings leveraged from the nuclear industry? The nuclear industry has had a long history of dealing with hydrogen in different forms and operating modes. Does the references we check out tell us how the nuclear industry could help the pipeline industry? Comments from either one of you?
Yeah, so my experience, in refinery work, we sometimes, look at nuclear codes. They're kind of the gold standard in analysis or design, because you have to, there's a lot of design by, first principles. And, sometimes we've used that type of analysis just to do a much better assessment of, a component of concern. But so I think there's always room for that, right? This is getting to that ASME section 8 division 2 part 5, where we're doing full finite element analysis on everything, that we're concerned with. And so if it's justified, yeah. And I think, about our work with Stantec, where we, and Jonathan, you're really an expert on this, but where we're looking at ways of doing, kind of the fast FEA to screen areas of concern. So we kind of get a hybrid benefit. And then areas that we really want to zero in, we spend a bit more time and do the full analysis.
Okay, we are now past the 1 o'clock local time, so I think we're going to wrap it up. So I really appreciate all the information, Christian and Jonathan, and for the audience, and the excellent questions. Again, apologize we couldn't get to all the answers. We will follow up offline. Hope everybody learned something unique today about this scenario, and thanks for joining or sharing your time with us, and we'll catch up with you next time. Take care, everyone.
My pleasure. Thank you. Bye-bye.